Thank you for joining our webinar today, focusing on parametric optimization and in particular the ANSYS DesignXplorer module. My name is Brian Miller and I'm joined today by my colleague Joel Thacker. So very quickly, what we hope to cover in the next 40 minutes is a very brief overview of wired analysis and our range of tools for optimization studies. We'll then hand you over to Joel, who will go into more detail, firstly talking about why we should do optimization and the benefits, and then talking through the process from what-if studies to developing response surfaces, and ultimately looking for trade-offs and finding optimum solutions. We'll then finish with a summary and a question and answer session. If at any time during this webinar you would like to ask any questions, then please type them using the questions panel on your GoToMeeting window, and we'll be pleased to try to answer them at the end. So for any of you who are not familiar with wired analysis, we're an independent engineering consultancy and we focus on providing three solutions. Firstly, multi-physics simulation. This is finite element analysis, CFD and electromagnetics. Safety and reliability engineering, software and services, and also an increasing focus on design and optimization techniques as we're describing today. And for all these three areas, we provide a complete service of software, training and consulting. Within our software solutions, we are a long-term channel partner for ANSYS, but we also have some other complementary products. FlowNext for 1D fluid simulation, Plaxis for nonlinear analysis of soils, two products for manufacturing simulation, Deform for metals and MoldFlow for injection molded plastics. We also have some other softwares for reliability engineering and engineering calculations, and obviously the theme of today is what we can offer in terms of optimization. So in this area, for parametric-based optimization, where we're changing design variables and try to identify the unique or optimum combination of variables, we offer three main solutions. Firstly, ANSYS DesignXplorer, which we'll be talking about today. Optimus, which is like ANSYS DesignXplorer, but is very much a generic general-purpose optimization package, which can be used with virtually any CAE or engineering calculation software. And it also allows you to control workflow management between various softwares as well. And in addition to looking at using optimization with virtual prototyping with simulation solutions, we also focus on how optimization can be applied to physical testing and accelerated life testing. And here we have Reliasoft, where we provide a DOE solution for helping companies decide on their test procedures and obviously interpreting the results. Just one note regarding both ANSYS DesignXplorer and Optimus. They both work closely with ANSYS, and they both can take advantage of the ANSYS parametric pack, which we may discuss a little bit more in later on. And this is ideal for enabling you to run a large number of simulations, even if you only have one solver. And of course, all our solutions are supported by our comprehensive training and consulting services. So now I'd like to pass you over to Joel, who will obviously now take you more on the journey towards how optimization can help your company.
Thanks, Brian. Good afternoon, folks. So like Brian said, we're going to start off talking a little bit about design optimization, why we care about it, and how we go about doing this in DesignXplorer. The first thing I want to mention over here is that we've all done design optimization. A lot of the problems that we see in engineering present an intuitive solution. We know what parameters and what variables are going to matter, and we have an idea of how we're going to steer the design. Sometimes, however, in multi-body analyses, more complicated multi-objective analyses, the parameters that matter are not very obvious. They require some sort of trade-offs. And this is where design optimization really comes into its own. Because what design optimization does is it formalizes the process. So it forces you to logically go through variables, to consider variables, to evaluate the variables, and then to eliminate them based on objective mathematical modeling. Moreover, it packages the designs that you see, the sampling points that you analyze, into a package that's easy for a designer to work with. So it's easy to disregard designs that are simply non-starters. The other use and main function of design optimization, of course, is the allocation of computational resources. What you don't want to be doing is running CFD jobs, FEA jobs that take a few hours to run on designs that simply aren't going to work. So design optimization basically focuses in on the design space that is worth looking at. Within DesignXplorer itself, we can take parameters from CAD models, and this includes external CAD packages like Autodesk, SolidWorks, etc. We can work with boundary conditions. We can work with engineering data, so yield strengths, Poisson's ratio, for example. It's also, being an ANSYS module, it's got the ability to talk through the entire ANSYS suite. So be that in CFD, in FEA, in EMAG, and explicit dynamics. And this is something I'll show you as we go through the presentation. We can work with inbuilt and derived variables. So by inbuilt variables, what I'm referring to are items like thermal strain, von Mises stresses, pressures, velocities, temperatures, but also derived variables. So in your industry, for example, you might have a certain variable that you care about, which is formulated on the basis of these derived variables. Thrust is a prime example, which is a function of mass flow rate and pressure and velocity. So you can optimize and parameterize thrust as a function of these basic variables. And again, DesignXplorer has a visualization toolkit that drives you towards a decision. We'll see again in the presentation, there are various ways to look at the data and to come to a logical conclusion. The general steps are, we start with a what-if analysis. This is our best guess. This is our initial optimization. It's a manual optimization. We then move to correlation studies, where we assess what actually matters to the analysis and to our output. We run a set of design of experiment studies, where we take the parameters that matter and put them and bind them within a design space. Look at the response surfaces to see how the input parameters can predict the output parameters based on mathematical models. We optimize either to a maximum or minimum or to a specific target. And then we've got to do the Six Sigma or robust design to make sure that something that works in the technical world will also work in the real world based on uncertainties like manufacturing and operators handling. So starting at the very top then, let's talk about what-if analysis, which is a type of manual optimization. This is based on best guess, really, where the user sets up discrete design points. It's ideal for assessing off-design scenarios, so for example, accident scenarios, or a bunch of serial simulations where the user does not have to interact with the GUI. An example of this is if we look at a simple valve analysis in CFD. So what we're going to do over here is investigate the pressure loss characteristics of a valve as a function of mass flow rate. So in CFX, we set up mass flow rate to be an input parameter, and we set up other expressions to be our output parameters that we're going to monitor. Schematically, with ANSYS, this is how it looks like. So you've got your CFD solution out here that is driven by DesignXplorer. And you'll notice there are items or parameters that are going out of DesignXplorer into CFD, and CFD is sending back output parameters into the DesignXplorer set. If you actually went into DesignXplorer window, this is what you would see. You'd see the parameter assignment. That's the mass flow rates being the input, and the velocities, loss coefficients being the outputs. You can set up multiple design points. Remember, again, this is manual, so you have to set up the design points over here. Once you set up the design points, you run the analyses. DesignXplorer goes through the analyses sequentially, and you obtain, for example, in this case, the loss coefficient or the pressure loss as a function of mass flow rate. One thing to note over here is that I've run a CFD analysis. I've run several CFD analyses over here without actually going into CFX. And this is quite handy if you've got, for example, one expert within the engineering group who knows how to set these models up, but you have several designers who want to look at what happens if I change this variable or I change that variable. They don't need to go into the CFD GUI. They can run DesignXplorer by just changing these parameters, and as long as they're working within the bounds of the model, then the CFD simulation or the FEA simulation should work. So that's a basic what-if analysis. The problem with a what-if analysis is that how do we know we've chosen the right parameters in the first place? There might be other parameters like temperature or diameter size that we haven't looked at and are strong players when you're looking at this design. If you imagine you start adding up all the parameters that really matter, what happens is that the design exploration based on what-if analysis is going to take a long time, and it's not really clear then how one parameter is affecting another parameter and where the trade-off really should be. Also, there's no way right now of knowing what the major driving parameters are, what's really influencing the design here or the outputs. This is where we move on to parameter correlation. What parameter correlation does basically is it asks the users to specify a whole range of input parameters, and it spits out the variables of interest by ranking. So it's best suited for multi-physics or multi-objective analyses. In the case, let's take a simple example where you have 3 independent variables, and they can vary from low, high, and a middle value. If you were monitoring a single output variable, you need about 27 simulations to understand how these parameters work against each other. Within DesignXplorer, specifically within parameter correlation, the software is smart enough to assign a set of random sample points. It's a type of Monte Carlo sampling. We call it Latin hypercube sampling. The difference between Monte Carlo and Latin hypercube is that if you consider 2 input parameters, x2 and x1, in Monte Carlo, one of these parameters might be a repeating parameter. Although the design points itself are different, each parameter might be repeated again. Also, there tends to be clustering of parameters. On the other hand, Latin hypercube, you get a more even distribution throughout the design space. And what's more is that no value of the input parameter is repeated again. So it's a better use of computational resources, and at the same time, you're getting, you're getting a broader understanding of the design space. So I've got another example over here, which is a cross test done by Explicit Dynamics and ANSYS. And the objective over here is to understand the stiffness of the can as a function of various parameters. These parameters are boundary condition parameters, like the velocity of the hammer falling down, or material strength parameters, like yield strength. There are also geometric entities like fillet radius and can thickness. This is a fairly nonlinear, very nonlinear problem, and it's hard to understand what are the driving forces over here and what actually matters. So when we run the parameter correlation, one of the first things we see is a correlation matrix. These are the results that we obtain. It looks like a heat map, and what you have is at the top, you've got your inputs, your first 4 inputs, which were the velocities and the geometric entities and the yield strength, and your outputs, which is your equivalent stress and plastic strain. the same deal on the y-axis or the vertical axis over here. The bit that we care about is this corner over here, where we want to assess how the inputs affect the outputs. The heat map is obviously color-coded, and red signifies that if we change an increase in yield strength drives an increase in equivalent stress. That's obvious because you're moving higher up the Young's modulus, basically. At the same time, we find that as we increase velocity, there is an inverse proportional relationship to equivalent plastic strain. So straight off the bat, we know these two are the driving parameters. The geometric parameters have no effect because if you look at them, they're in the gray area, and the numerical value associated with them is nearly zero. So again, the closer you are to positive or a negative one, the stronger the relationship between the input and the output. You can look at this via sensitivity charts also. So again, if you're looking at equivalent stress, you can see that yield strength matters most. And if you're looking at equivalent plastic strain, you can see that an increase in velocity actually drives the plastic strain to go down. Another feature within DesignXplorer is the correlation scatter. In some instances, you might find that the input and the output follow a quadratic or a linear relationship. In this case over here, it's quite easy to see that it doesn't really follow either. But like I said before, for equivalent plastic strain, for example, it can follow one of the two best fit curves. There's an advantage to this in that once you know that it follows a trend line, you can predict future behavior of your product or of your output. Okay, so parameter correlation, what it does is assesses the weight of each input parameter and tells you what matters, what doesn't. So from a parameter space of, let's say, 10 variables, you narrowed it down to 5 or 7 variables. But what you haven't really done is address the bounds of the design envelope. All you know right now are the variables that matter. This is where designer experiments comes in. So it takes the weighted inputs from parameter correlation and distributes the sample point within the bounded design space that the user has prescribed. Once the DOE is complete, you obtain a mathematical model, which is a response surface. Remember, DOE is actually running discrete design points. And what a response surface is doing is interpolating between these design points to come up with a smooth and continuous mathematical formulation that you can use to find the output behavior at other design points that you haven't actually analyzed. So I've got a multi-physics simulation example over here where CFD is linked to thermal and static structural FEA. So we've got fluid that enters through the channel out here. It's heated via these heaters and it exits past the pipe over here. And what we're interested in is keeping the outlet temperature at a certain value, and also we want to assess what the thermal deformations are on these support structures within the channel. So once we've described the upper and lower bounds of the input parameter, various algorithms exist within DesignXplorer to optimize the sampling points within the design space. One of them is a central composite design. This is good if you want, your design or your sampling points to be gathered towards a certain parameter. We've got box designs. We've got Latin hypercube. Again, we can see how evenly spread and more spread the design points are. Or we've got optimal spacing design. There are a few more which I won't go into here. But again, with optimal spacing design, you can see that you get a larger spread of the design points. And again, this is helpful because you're running fewer simulations, but you're getting the most out of your study. Once you actually run the DOE, like I said, you obtain response surfaces, and these are nothing more than mathematical formulations that interpolate between the design points. Depending on your response surface, you might have a very simple quadratic or linear response surface, or you might have a very nonlinear exponential surface. And we've got several other models like Kriging, neural networks that can handle higher order response surfaces. Okay, so once we've got a response surface, it's important to actually check the validity of this response surface. The last thing you want to do is take the response surface that you've got, go ahead and design a product, and then realize that your response surface itself was not accurate. So within DesignXplorer, we can verify how good a response surface is. So in this case over here, I've picked an arbitrary value of inlet velocity, temperature, and heater temperature. And based on the response surface, I've got these values, these output values in blue. I can set this actually as a design point now, where ANSYS goes back and physically solves this design point, and you can see that the results closely match the response surface. So this is vital because it tells me, okay, if I'm going to move forward with this response surface and I'm going to design something with this response surface, it's actually predicting the output behavior correctly. So so far, what we've done is identify the relevant parameters in parameter correlation, developed a method to predict output behavior via a mathematical model in DOE and response surfaces. Now, using this information, because we have a way of predicting the output, what we want to do is use this mathematical model to generate an optimal design. And this is where optimization comes in. So if we were to drive optimization within ANSYS, we'd go into the optimization tool. And the first thing we need to do is discuss what type of optimization we want to do. Is it highly nonlinear? Is it linear? Are we looking for a single objective? Are we looking for multiple objectives? And these are the options you have, basically. In our case, we're going to go for a multi-objective genetic algorithm. Once we've set that up, we say how many sample points we want to analyze, how many per iteration, and the next important thing is the allowable period or percentage. So within any design optimization exercise, if you have multiple objectives, there's a very slim chance that you're going to achieve a design that meets all these objectives perfectly. There's always going to be a trade-off study somewhere. There comes a point within a design optimization exercise where if you change one of the parameters, try to make one of the parameters better, you're sacrificing one of the other output parameters. At this point, we call the solution Pareto efficient. And what the Pareto percentage is basically is a ratio of the number of desired Pareto points to the number of samples that you're analyzing within DesignXplorer. So we keep that at 70%. The last thing we need to do then is to actually ask Design Modeler to give us n number of possible candidates. So in this case, we've chosen 5 candidates. Is what we want DesignXplorer to give us back. We need to set our objectives and constraints. So when we go to our parameter, we can either set up a constraint on an input parameter or an output parameter. So these parameters are listed as you see on the screen. The first parameter that we're going to constrain is the outlet temperature. So we choose that. And what we're going to do is rather than minimize or maximize that, we're going to set a specific target for the outlet temperature. So we go ahead and select seek target, and then we give it a value. In our case, we're going to give it a value of 65 Celsius. The next parameter is the total deformation, and we're going to bound it by an upper bound, which is 200 odd micrometers. And the next parameter is the thermal strain, which we're going to bind again by an upper bound of 150 micrometers. Okay, let's talk a little bit about these bounds. You can obviously give an upper bound, so say a parameter should never go beyond this limit. You can give a lower bound. You can say the parameter has to reach this limit, or you can say a parameter can lie anywhere between a lower or an upper bound. So in our case, we're going to go with the upper bound of 150 micrometers. You've got our input parameters. We can change the lower and upper bounds of the input parameters because, remember, we're trying to optimize, so we can zone into a specific area. Once we've got our objectives and constraints, we simply go ahead and hit the optimization button. And ANSYS will go ahead and try and find us 5 design candidates that meet our requirements. So here they are, our 5 design candidates. ANSYS DesignXplorer works on a ranking system. So 3 stars signifies that all the criteria, well, the criteria has been met, the objective has been met. 3 crosses signifies that this is a failed design and it's not going to work. A gray dash means that it's neutral. This is as good as it's going to get. So you can see across the 5 candidates over there, we reach our target of total deformation and thermal strain, but we don't really meet our target of outlet temperature. We specified 65 degrees, but we've got 60 odd degrees over here. And this is as good as it's going to get, basically, for us. So if we plot that in a 3D space, on a 3D graph, we get the points, we get the design points and the values. And you've probably seen this in 3D or in 2D format, and this is the Pareto front graphs. The blue points signify candidates that are feasible, and the red points signify candidates that are non-feasible, and the gray circles are those that are simple non-starters to begin with. One thing to take away from here now is the fact that there's more than one design point that meets the criteria. So this is where the subjective trade-offs come in between the product and the designer. There might be other non-technical factors that affect the performance, such as manufacturing variables, operator handling, the quality of the material, for example. Either way, once we send a product out to the market and it's operating out in the field, we need a quantifiable way of stating that this product is going to work, and we need to deliver that as a numerical value. And that's where Six Sigma or robust design comes into play. So as I said before, most systems are designed to a technical spec, but they won't always meet that technical spec, simply because there are factors outside the technical remit that play on the design, basically. So we need a quantifiable way to measure the probability of success based on the uncertainties in the input parameters. So for the case that we have, we've given a normal distribution to the inlet velocity, saying we would like to receive 11 meters per second, but there's a chance that it could go either side of 11 meters per second. It doesn't have to be a normal distribution. It could be a triangular distribution weighted towards one value, or it could be a uniform distribution. Once we run the Six Sigma analysis, we get the graph shown on the screen over here, which basically tells us the probability of it meeting our design criteria. For those who are unfamiliar with the Six Sigma standard, it basically states 3.4 out of 1 million instances are allowed to fall outside the design specification. For argument's sake, let's say our maximum total deformation was allowed to be less than equal to 270 micrometers. The graph actually shows that 3.4 out of 1 million will have a total deformation value of less than 290 micrometers, which is greater than 270 micrometers, obviously. So what this means is that although we've technically satisfied the design, we don't have a robust design. It's failed the Six Sigma criteria due to variabilities in manufacturing or other input parameters. Okay, to wrap up over here on what we've done so far, if we started at the top with a what-if analysis, it's a best guess analysis. So what I've got over here are green, red, and orange circles. The green circles are those variables which are high influence and they drive the design. Red are those that don't matter, and orange are moderately influenced. In a what-if analysis, because you're doing a best guess optimization exercise, there might be variables of high influence that you've completely missed out. while you've added in variables of no influence whatsoever. The relative sizes of these circles is the parameter space that you need to be considering. You will probably reach a design using a what-if analysis. You'll reach a working design. Is that the best design? Probably not. The next best thing is a correlation exercise where you identify variables that matter and you move that out of the design space. Again, once you've done a correlation exercise, you obtain a technically feasible design. It's a better design because you at least know what matters to and what's driving the design output. A more thorough way is to do a DOE or response surface analysis where you hone in to specific parameters within a design space. So you give an upper and a lower bound and you find out how the output actually behaves for the design space sampling points that you mentioned and for other points also for the future. You then optimize to either a seeking target or a minimum or a maximum. But what that also says is that based on the response surface, you then realize that you don't actually need to go through the entire design space. You can choose to omit some of the variables. You only need some of the range of the design space. Once you've actually got an optimized design, you run a Six Sigma analysis to take into account variability of products. A Six Sigma design is going to give you a technically optimal design and a robust design. Starting at the top, what-if analysis is your best guess and is based on experience. Correlation is an educated guess, and again, it's based on experience. A Six Sigma design, though, is based on objective mathematical modeling and subjective trade-offs that are done by the user or the designer. I'm going to hand it back now to Brian, who's going to wrap up and take any questions.
Okay, thank you, Joel. So hopefully in the last 30 minutes or so, we'll be able to give you a bit of a flavour and an overview of parametric optimization and the techniques available, and how you can use ANSYS DesignXplorer as part of that process. So generally, what we like to feel is that by using optimization software, you can enable a formal process for exploring design alternatives rather than just a best-to-guess approach. And indeed, if you take on board design of experiments methodology, then you're able to facilitate a search and achieve an optimum solution. DesignXplorer, as you've seen today, is a simple add-on for ANSYS Workbench, which works for the range of solvers, FEA, CFD, and electromagnetics. And we believe it helps simplify and also speed up that formal optimization process. And more specifically, some of the benefits of DesignXplorer we have seen include providing a structured workflow. So when we've been looking at the optimizations today, there's been a number of CFD or FEA simulations that have gone on in the background. DesignXplorer allows that to happen very quickly and efficiently from a user perspective. With the associativity built into ANSYS, we can automatically make geometric changes or parameter changes behind the scenes and essentially allow you to use DesignXplorer as an interface for driving those simulations. What we've also talked about is the sampling of designing points to understand which combinations of parameters you should use when running your simulations. And a range of techniques and a range of algorithms within DesignXplorer to help you choose those sampling points intelligently to both efficiently model the interactions you're likely to get between your parameters, to efficiently understand what's going to influence the design and obviously hopefully drive to an optimum, whilst also be able to minimize the number of simulations you actually have to run. Obviously, when you do a parametric optimization and you run a number of simulations, then you're going to be faced with a lot of data, a lot of simulation results. DesignXplorer is ideal for enabling you to basically visualize and identify the relationships from those simulations which are important from a design perspective. So you can quickly narrow down on the results and the correlation with the variables, including trade-offs and all the different choices you have with those variables, to really interpret the data quickly and efficiently. And ultimately, you can then, through the various optimization algorithms built into DesignXplorer, seek combinations of parameters which will both hopefully, as Joel mentioned earlier, find a design which performs very well and is also robust in terms of the uncertainties in the real world. And the final point, obviously a lot of focus today has been on the DesignXplorer add-on for ANSYS, but we also have Optimus as an alternative solution for those of you who perhaps don't use ANSYS for all your CAE or other engineering calculations, and also would like to use a system for connecting all those softwares together as well. So we find ANSYS DesignXplorer and Optimus complementary in many regards, depending on what type of optimization and workflow management you're hoping to achieve. So finally, before we take questions, just a few points on perhaps where you may want to go from here. Obviously, we'll be delighted to have some discussions with you to discuss how DesignXplorer or indeed our other optimization solutions may benefit your design processes. But you may also want to consider attending one of our training courses on ANSYS DesignXplorer if you're already an ANSYS user. And indeed, we can also help you evaluate DesignXplorer or other optimization solutions themselves through an evaluation license. And finally, through our services, we would also be very pleased to provide a sample service project where we can focus on one of your current designs, hopefully improve the performance, and enable you to test the value of the optimization methodology we have discussed today.